This video will be about double replacement reactions. Firstly, double replacement is going to involve two ionic compounds that are dissolved in water. This is known as aqueous. When they get dissolved, they what we call dissociate in water and float around as ions. The water pulls apart the ionic crystal, and then they exist in solution as ions. We'll kind of draw a picture of that in a bit. When we mix the two solutions of our reactants, these ions are free to interact with previous ions they were not around. And so we kind of pair up a cation and an anion to make a different pairing of an ionic formula that wasn't previously made. When the new pairing of cation and anion come together, they can either form an ionic crystal and become insoluble, settle out of the solution as a precipitate, or continue to stay as ions in solution because they will not be forming an ionic crystal in solution. And so that's our goal of a double replacement. We're going to kind of look a little bit more into what this all means. So firstly, this is the general format. We have our ionic compound. So this will be A is being positive, B is a negative ion, C is a positive, and D is a negative. So ionic being cation with anion plus another ionic that has cation with anion. The goal in a double replacement is to switch things up. And so cation A, as we will see it here, can only really switch in one way to make a new ionic compound. And that means it'll have to pair with anion D. The reason for that is we want to make a new ionic compound. And we can't put A and C together because they're both positively charged. We cannot put B and D together because they're both negatively charged. We can't put A and B together because they were already together. So the only new combination that we can do is A with D, and then similarly C and B together. Now notice the little kind of arrows here are showing that we're going to be putting inside and outside together. So the outside ones, this positive with this negative. Pair up over here. Doesn't really matter the order on either side of the plus, just that those get combined. And then that also leaves this cation here to go with this anion. And so I call this the inside-outside method. Notice I did flip the order though, so it wasn't B and then C, but it is still cation first. So feel free to fill in the notes. I'm going to add another section of notes right here and pause really quick while I write those down. When we make these new compounds, it's important that we make the correct ionic formula for the charges of the ions involved. Often when students do the inside-outside method, they move subscripts that should not move with the kind of new combination. And we'll explain more about this in terms of how to pair up charges. But overall, you want to make sure that when you are creating a new ionic compound, that it would be the correct ionic compound based on the charges of the things involved. So we're going to look a little bit more here into what this all means. So in our first thing, we have sodium. Now I recommend kind of looking up what the charge of all of these is. Sodium hydroxide, both of those have a 1 charge. And then we have silver, also a 1 charge, and nitrate, also a 1 charge. It may even help to kind of box off what is your cation and what is your anion here, so you are making sure to move the right things. Now, one thing I'm going to point out here that'll come up a little bit more when we have more complicated formula. All of these are a 1 charge, so it's not that complicated in terms of recombining. But this 3 is part of nitrate. So that would be a case where we would move that 3 over. That 3 did not come from silver. We can see the charge of silver is 1. So that 3 is part of nitrate. So when we repair up, that needs to stay as part of it. We have in our first beaker, sodium and hydroxide. And then in our other beaker, we have silver and nitrate. These are, as I said before, dissociated ions. So they are no longer attracted to each other in a crystal solid structure, but water has pulled them apart and now they're floating independently as charged ions. And so when we mix things together, we're going to see, firstly, that sodium has one option here. And that option is to pair with nitrate. So we have Na coming together with NO3. Now, sodium has a +1 charge. Nitrate, notice I moved the 3, has a -1 charge. So the correct formula here is, in fact, NaNO3. The other combo that we're going to get is silver. I'm going to put silver first because it's positive. I am color coding, not in the beakers, but color coding that red is my cation, it's always going to be first, and then blue is anion, always second. And then we would put that with hydroxide. These also have a 1 charge each, so that would be the correct formula. In this case, it is already balanced. I'm not going to go over that right now, but this would be something that you would need to consider when you are doing reaction, is if it is balanced or not. Looking now at our beaker, we're going to find that everything gets mixed together. One of these, and I'll tell you which one here, is sodium hydroxide is going to come together as, didn't want to do that. Sodium hydroxide is going to come together as a precipitate, meaning when it finds the ions here, when sodium finds hydroxide, it does not want to dissolve any longer. It forms a crystal structure, it attracts itself, and it comes out of solution and sinks to the bottom as a solid. Sodium and nitrate, however, do not do this. They do not come together and say, we will no longer dissolve. They stay dissolved. They stay aqueous. The goal of all double replacement reactions is to find a precipitate. If when you mix these two things together, everything stays in solution, meaning no solid forms, then no reaction has actually occurred. You need to form a new product, a solid product, to consider the double replacement reaction a success. So if you have what I call ion soup, where everything is just still floating around, then no reaction has actually taken place. You need to form at least one. You could form two, although it's more difficult. You need to form at least one solid precipitate. So that's the last little bit here. How do I know that a reaction actually occurred? So if a precipitate, a solid, forms, then a reaction has occurred. If both products stay dissolved, then no reaction has occurred. I'm going to fill in some more notes, and they'll pop up in a second here, and then you can finish copying those down. Just kind of filled in a little bit of what I've said. So if a precipitate, a solid, forms, then a reaction has in fact occurred. So when these two ions find each other and attract, they are not soluble, this will sink to the bottom. If, however, as I said, both products stay dissolved, aqueous, then no reaction has actually taken place. And that's the general background of what double replacement is, in terms of our notes that we'll be taking on it.